One of the things that's often very nice to do is to convert between the exponential form and the logarithmic form. The way we do this is we preserve the base and then we switch the input and the output. So for example, on an exponential, 6 squared is equal to 36. So an input of 2 gives an output of 36. Now, when I switch over to logarithm form, that's going to be a log base 6, except now on the logarithm, the 36 is the input and the output is the 2. Here we had the input of 2, the output of 36. Here it's an input of 36 and an output of 2, but now it's on a logarithm function with a base of 6. Here's another exponential. 11 to the 0 equals 1. So this on a base of 11 takes in 0 and gives out 1. So on the exponential function, it's going to take in 1 and give out 0, but it's a logarithm base 11 because the base on my exponential had a base of 11. Now here's one with some fractions in it. This is an exponential with a base of 1/4. It takes in 3 and gives out 1/64. So over here on the logarithm function, it's the same base of 1/4, but it takes in 1/64 and it gives out 3. When you go from exponential to logarithm, my inputs and outputs switch around. And probably the hardest thing to remember is where did the inputs go? On the exponentials, it's in the power. In the logarithms, it's what's inside of parentheses. And don't get stuck on being inside of the parentheses because a lot of the time people do not put these parentheses on when they write down logarithms. They'll just write log base 11 of 1, not parentheses 1. I tend to put on the parentheses all the time, but your textbook tends to leave them out quite a bit. Now we can go back the other way. So here's a log base 5. It takes in 25 and gives out 2. So when I convert it over to an exponential, it'll have a base of 5. It'll take in the 2 and give out the 25, and it even makes sense because 5 squared is equal to 25. If I have log base 9 of 1/9 equals -1, that means this takes in 1/9 and gives out -1. So when I convert it over to an exponential with a base of 9, it'll take in -1 and give out 1/9. If I have log base 10 of 1,000 equals 3, that means the input is 1,000, the output is 3. So when I convert it to an exponential with a base of 10, that's going to take in the 3 and give out the 1,000. And again, notice all of these exponentials make sense here. 10 cubed is 1,000. You can certainly use your calculator to find logarithms to the base 10. Such logarithms are typically called common logarithms and are denoted without a base. When you think log base 10, that's exactly the same as just log with no base. That's a button on your calculator. Typically it says either LOG or LOGX after it. And you can go ahead and use that to actually compute common logarithms. For instance, if you said LOG of 100 and hit enter, you should get 2. And that's because when I convert that to exponential form, 10 squared is equal to 100. If you were to do log of 1 over 100, you should get -2. And that's because when I convert that to an exponential, 10 raised to the -2 is 1/100th, right? The input of -2 gives 1/100th because on the common log, an input of 1 over 100 gave -2. Now, there are other logarithms that are in common use and have shorthand notations. One of those are natural logarithms. Natural logarithms are simply a log with a base of e. Remember, e is that number that's approximately 2.71 that we talked about in the previous section. Instead of writing out log base e, the shorthand notation for that is just to write ln of x, and the ln stands for natural logarithm. I think it probably is not NL because it probably came from some Romance language where it was like Logarithm natural. y equals ln of x is equivalent to the exponential form with a base of e, output of x, input of y, so x equals e to the y. Your calculator also has a button for calculating natural logs, and typically it says ln of x on it, or ln. If you press that button, put in your number and hit enter, it'll calculate the natural logarithm of the number. And those are the two basic buttons, the ln button and the log button. Any other base logarithm, we actually have to use a change of base formula to do, and we'll talk about that in a later section. So that natural logarithm function comes in handy when you're working with the formula s equals p times e to the rt. Remember, that's that formula we talked about in the previous section. This gives me the future value s of an investment where p dollars were invested for t years at a continuous interest rate r. You can use this formula even when you're not talking about investments. If you're talking about populations that are growing at a continuous rate, this would also apply. But now instead of thinking as p as your original amount of money, you would think of p as your original population. So let's go ahead and use that formula, and let's figure how long will it take us to double our investment at a continuous interest rate of 4%. So let's start with that formula, s equals p times e to the rt. And double my initial investment means that the original p has to become 2p. So we're going to set s equal to 2p in this formula. I've also gone ahead and put in the 4%, and in this particular formula you need to put it in as a decimal. So we get 2p equals p e to the 0.04 times t. Now if we divide both sides by p, that drops out. So basically that's telling me the initial amount doesn't matter. As long as I want to double my money, it's always the same amount of time. So now I'm left with 2 equals e to the 0.04 t. And if I convert that over to a natural logarithm, remember a base of e will go to ln. The output on the exponential was 2, so that becomes the input on the ln. The input on the exponential was this group of symbols, 0.04t, so that now becomes the output from the logarithm. To get the t by itself, I need to divide both sides by 0.04, so I get ln of 2 divided by the interest rate, 0.04, equals t. And if I work that out on my calculator, I'll get that it's approximately 17.3, and in this case we're talking about years. So if you have a 4% interest rate, it'll take you 17.3 years approximately to double your money. Now in general, we can find the amount of time it takes to double our money by generalizing this procedure. So again, we'll start with s equals p times e to the rt. We want to go ahead and start with p and double our money, but this time I'm not going to put any value in for r because we're generalizing this. We divide both sides by p. I get 2 equals e to the rt. And if I convert it over to a logarithm, I get ln of 2 equals rt, because the output of 2 becomes the input on the ln, and the input of rt on the e becomes the output from the ln. We're trying to solve this for t, so we're going to go ahead and divide both sides by r. So I get ln of 2 divided by r, the interest rate, gives me the time. So if you want to double your money, or if this was a problem talking about populations, if you wanted to double your population, this formula would tell you how long it takes. And if you wanted to triple your money, we just change the 2p up here to 3p and follow through the numbers, and we get something like ln of 3 over r equals 2. So there are lots of little nuances we can make if the problem changes a little bit.